Have you ever reused cooking oil and noticed something strange? The first time you fry with fresh oil, everything comes out golden, crisp, and clean. But by the third or fourth time, the same oil starts acting different. Your fries brown too fast. Your food tastes heavier. The kitchen smells sharper. And sometimes the oil itself turns darker, thicker, almost tired. At first, it seems simple. Oil is oil, right? If you strain out the crumbs and store it properly, it should still be the same thing sitting there in the bottle. But here's the strange part. It isn't. That liquid in your pan may look familiar, but chemically, it has already started becoming something else. And once that process begins, there's no turning it back. So what exactly happens to cooking oil after you use it? Why does it slowly change? And what's going on inside that bubbling pan that transforms something so ordinary into something completely different? Today, we're uncovering the surprising truth behind why your reused cooking oil isn't really the same oil anymore. Most people believe cooking oil just gets dirty. That's the common explanation. Food particles fall into it. Tiny burnt crumbs float around. Those leftovers make the oil darker and affect the taste. And yes, that's partly true. If you filter the oil, you can remove a lot of those particles. That's why many people assume filtered oil is basically fresh again. Logical. Simple. Problem solved. Except it isn't. Because even perfectly filtered oil still changes. You can remove the visible dirt, but you can't remove what heat has already done to the oil itself. And this is where things get fascinating. To understand what's happening, imagine cooking oil as a carefully built tower made of tiny building blocks. When the oil is fresh, that tower is stable. Everything is arranged neatly. Its molecules are intact, which is why it behaves predictably when heated. It gets hot. It transfers heat efficiently. It helps food crisp up beautifully. But the moment you heat it for frying, especially at high temperatures, that tower starts taking damage. At first, it's small. A few cracks, a little stress, nothing obvious. But every time you heat the oil again, the damage grows. And eventually, the structure begins to collapse. This happens because cooking oil is mostly made of fat molecules called triglycerides. You don't need to remember the name. Just think of them as tiny chains. When oil gets very hot, those chains begin to break apart. And once they break, they don't simply reconnect. Instead, they form entirely new compounds. Some harmless, some unpleasant, some that change the way the oil looks, smells, and tastes. This is why reused oil behaves differently. It has literally become chemically altered. It's no longer the same collection of molecules you started with. It has been rewritten by heat. But heat alone isn't the only culprit. There are actually 3 invisible enemies attacking your oil every time you fry. The first is oxidation. This happens when hot oil reacts with oxygen in the air. It's a little like what happens when you slice an apple and leave it out. It slowly changes. Only with oil, the reaction is happening faster because heat speeds everything up. Oxidation creates compounds that make oil smell stale or sharp. That old fryer smell? That's chemistry happening in real time. The second enemy is hydrolysis. Sounds complicated, but it's surprisingly simple. When you fry food, especially frozen or wet food, water escapes into the oil. And oil hates water. That water breaks apart some of the oil molecules, creating free fatty acids. These make the oil less stable and more likely to smoke. That's why reused oil often starts smoking at lower temperatures than fresh oil. It's becoming more fragile. The third enemy is polymerization. And this is where things get really weird. Under repeated heat, some broken oil molecules start linking together into larger chains. Imagine melted sugar hardening into sticky caramel. Something similar happens inside old cooking oil. The molecules join up, making the oil thicker and stickier. That's why reused oil sometimes feels heavier or leaves a gummy layer on pans. It's slowly turning into a different substance altogether. So every time you reuse cooking oil, these 3 processes are happening at once. Oxidation, hydrolysis, polymerization. like three tiny wrecking crews, all reshaping the oil molecule by molecule. And here's the twist. This transformation starts much sooner than most people think. Not after 10 uses. Not after the oil turns black. Sometimes after just one frying session. Especially if the temperature got too high. This raises a bigger question. If oil changes so quickly, why does fresh fried food taste so good in the first place? Why does oil handle intense heat at all? The answer lies in something called the smoke point. Every cooking oil has a temperature where it begins to break down rapidly. Below that point, it performs well. Above it, the molecular damage speeds up dramatically. Different oils have different limits. This is why deep frying is often done with oils like peanut, sunflower, or canola oil. They can tolerate higher heat before breaking apart. Olive oil, especially extra virgin olive oil, has many flavorful natural compounds. Great for drizzling. Not ideal for repeated deep frying. It's like using a sports car for off-road driving. Possible? Sure. Efficient? Not really. And humans figured this out long before we understood the chemistry. Across history, different cultures developed frying traditions based on whatever fats handled heat best. In parts of Asia, peanut oil became popular. In West Africa, palm oil has been widely used for generations. In Europe, animal fats like lard were common for centuries. People didn't know about triglycerides or oxidation. They just knew which oils held up better. Experience taught them what science would later explain. Even massive fast food chains obsess over this. Industrial kitchens constantly test their fryer oil. Not because they're being picky, because oil quality changes everything. Taste, texture, color, even cooking time. Some restaurants use electronic sensors to measure how degraded their oil has become. That's how serious this transformation is. And here's a surprising fact. The dark color of reused oil doesn't always tell the full story. Sometimes oil can look relatively clean while being chemically degraded. And sometimes darker oil is simply carrying pigments from food. So your eyes alone can't always judge it. Your nose is usually better. If the oil smells rancid, sharp, bitter, or strangely fishy, its chemistry has shifted. It's telling you something. So let's return to the original question. Why isn't your reused cooking oil the same oil anymore? Because every time it's heated, its molecules are being attacked and rearranged. Heat breaks them. Oxygen reacts with them. Water weakens them. And some fragments bond into larger, heavier compounds. The oil you started with slowly transforms into a new chemical mixture. It may still look like oil. It may still fry food. But at the molecular level, it has changed. And once those changes happen, filtering can't undo them. You can strain out crumbs. You can remove visible debris. But you can't reverse chemistry. That bottle of reused oil is really a record of every meal it has cooked. Every batch of fries. Every piece of chicken. Every second spent bubbling at high heat. It carries that history inside its molecules. And maybe that's the fascinating part. Something as ordinary as cooking oil seems so simple. Just a liquid in a bottle. But hidden inside it is an entire world of transformation. A reminder that even the most everyday things are constantly changing in ways we can't see. So next time you pour used oil back into a container, take a closer look. You're not storing the same oil. You're storing the story of what heat has done to it. And now I'm curious. What's another everyday kitchen mystery you've always wondered about? Drop it in the comments. And if you enjoy uncovering the hidden science behind ordinary things, subscribe for more. Because sometimes the most familiar objects hide the most surprising secrets.